This video will help you successfully complete Punnett squares for one genetic trait. It will be helpful for you to have a piece of paper with 4 Punnett squares drawn on it. Just draw a big square with a horizontal and vertical line, like the one you see here. Before we begin, we need to understand a few key terms. Genotype is the genes for the trait we are interested in. Genotype is shown with 2 letters since the organism inherits one gene from mom and one gene from dad. Uppercase letters are for the dominant form of the trait, and lowercase letters are for the recessive form of the trait. If the organism has a homozygous genotype, then both of the genes are the same, like 2 uppercase letters or 2 lowercase letters. If the organism has a heterozygous genotype, the letters are different. In this case, our sheep is homozygous dominant. The phenotype, on the other hand, is the physical expression of the trait, or how it appears. Our sheep's phenotype is white wool. Now we are going to cross 2 sheep with different genotypes. The white sheep is homozygous dominant for wool color, which gives him a genotype of big W and a phenotype of white wool. The black sheep is homozygous recessive for wool color, which gives her a genotype of little w and little w for a phenotype of black wool. What do you think will happen? Back in Mendel's day, people thought this cross should produce equal numbers of black and white sheep. Rather than just guessing, we will use a Punnett square to help us determine the probability or likelihood of producing different genotypes and phenotypes when crossing our sheep. Let's set the first Punnett square up. On the left side of your square, write the genotype for parent number 1, which is the white sheep. Remember, he is homozygous dominant, so both letters are uppercase. Use the letter W because white is the dominant form of the gene. Now on the top of the square, write the genotype for parent number 2, the black sheep. Make sure you write your W's distinctly smaller so you can tell the difference between them. Now it's time to cross. Starting on the left side, follow the red arrows and write the letter on the left side of the square in each box as you move horizontally across. You should have an uppercase W in each box. Next, from the top of the square, follow the blue arrows and write the lowercase w in the boxes moving vertically downward. You should have a lowercase w next to each uppercase W in each square of the box. Look at the Punnett square now. All the boxes should have the same genotype, big W, little w. This is the heterozygous genotype because the letters are different. But what will the sheep look like? Good question. Since the dominant trait is white wool, all the sheep are white. Dominant traits hide or mask the recessive trait in the phenotype, so sheep with the heterozygous genotype, big W, little w, will always be white. Also, we can see from the results of our cross that all offspring from these 2 sheep will be heterozygous, so there is no chance of producing a black sheep from this cross, even though the mother had black wool. So where did the black wool gene go? Can we ever get more black sheep? Wow, you have great questions. Let's find out what happens if we cross heterozygous sheep. Our heterozygous sheep both have big W, little w genotypes. We recall that since each sheep has one dominant gene, the phenotype shown is the dominant one, or the white wool. People in Mendel's day thought that crossing 2 white sheep should always produce white lambs. What do you think? It seems reasonable based on what we can see, but also we know that sheep carry a recessive gene that we can't see. It's time to set up your next Punnett square. Remember that parent number 1 is written on the left side of the box and parent number 2 is on the top. Setting it up the same way every time will help you do it correctly. This time, the genotypes on the outside of the box are exactly the same, big W, little w. How will that affect our cross? Last time, all the offspring were the same genotype, but this one looks like it will be different. Starting on the left side, follow the red arrows to fill out the box with a gene from parent number 1. Be careful not to get mixed up. The boxes on the top row should have big W's in them. The boxes on the bottom row should have little w's in them. Next, follow the blue arrows from the top of the box. The boxes in the left column should have a big W in them, and the boxes in the right column should have small w's in them. What are your results? If you did your square correctly, it should look like mine. When we add the phenotypes to our Punnett square, we can see that most of the sheep will have the dominant phenotype, white wool. In fact, for every 4 lambs produced, we can predict that 3 will have white wool and 1 will have black wool. This is the same kind of results Gregor Mendel got with his pea plants. He saw that the dominant phenotype appeared in a 3-to-1 ratio, just like our sheep. Here are the final results of our cross of 2 heterozygous sheep. For genotype, we have a 25% chance of getting homozygous dominant or homozygous recessive offspring. We have a 50% chance of getting heterozygous offspring. Phenotype, however, is a different story. Any genotype that has one dominant gene will have the dominant phenotype. So, we have a 75% chance of getting lambs with white wool. Only the recessive genotype will have black wool, so there's only a 25% chance of getting black lambs. So does this mean that every time two heterozygous sheep mate, they will have 4 lambs, 1 black, and 3 white? No! Sheep don't always have 4 lambs at once. In fact, they usually only have 1 or 2 at a time. What the Punnett Square means is that when sheep that have heterozygous genes for wool mate, there is a 75% chance of getting a lamb with white wool and a 25% chance of getting a lamb with black wool. The probability is the same for every lamb, no matter how many lambs are born. Phew, I'm getting really sick of sheep. Now that you are feeling more confident with Punnett Squares, let's do a different cross, this time with hamsters. In hamsters, blonde fur is dominant and brown fur is recessive. Our parents-to-be are both homozygous, one's dominant and the other's recessive. I want you to predict what will happen in this cross. Think back to when we crossed our first sheep parents. Pause the video and do the cross on your paper. Were you right? I bet you were. Just like before when we crossed 2 homozygous parents, the offspring can only be one genotype. In this case, just like in our first sheep cross, all our offspring hamsters will have a heterozygous genotype or big B little b. So what will the hamsters look like? I'll give you a second to think about it. Okay, time's up. That's right, all the baby hamsters will be blonde because the dominant trait will hide the recessive one. Here are the results of our hamster cross. For a homozygous dominant parent and a homozygous recessive parent, the offspring have a 100% chance of having a heterozygous genotype. They also have a 100% chance of having a phenotype of blonde fur. Let's see how good you have become at doing Punnett Squares. Here's your next cross. We have 2 heterozygous blonde hamsters. I want you to draw and set up your Punnett Squares, remembering where to put each of the parents. Go ahead and do the cross. Pause the recording so you have time to finish. Time to check your work. Your square should look like this one if you did it correctly. Remember that even though one of the heterozygous squares is little b big B and the other one is big B little b, they both mean the same thing. No matter what order you write the letters, if they are different, the genotype is heterozygous. You may hear heterozygous referred to as hybrid. That's okay. Hybrid and heterozygous mean the same thing, a genotype that has 2 different genes. When we add the phenotypes to our square, we can see that familiar 3-to-1 ratio again. 3 of our boxes contain blonde hamsters, and 1 box contains a brown hamster, even though both parents were blonde. Because we understand genetics, we know that 2 blonde hamsters can have a brown baby. It's just not as common as a blonde baby. So we see the final results of our cross of heterozygous hamsters. For genotype, there is a 25% chance of having offspring with homozygous genotype, either dominant or recessive. There is a 50% chance of having the heterozygous genotype. The probability for the phenotype is 75% chance of blonde and 25% chance of brown hamsters. When you are doing Punnett Square problems, make sure you write out percentages for both the genotype and phenotype and that both sets add up to 100%. Hopefully by now you are feeling really good about Punnett Squares. You should, because you are now a Punnett Square master. Sorry, the cape and goggles don't come with the title. But you can keep that satisfying sense of accomplishment and take your new skills with you back to science class. Thanks for watching, and good luck with genetics.